Hey, future AP Physics C students. This is the first of two videos I'm putting together for you so you can familiarize yourself with the calculus that we're going to be using from the very start of the course. So this first video is going to be all about derivatives, and the next video I post will be about integrals. Okay, so what is a derivative? You've probably investigated these mathematical objects in your pre-calc course or your calculus course for sure. But the derivative of a function is another function which gives the rate of change of the original function. And when I say rate of change, I mean the rate at which the original function output varies with respect to changing the input variable. So if I have a function, let's say f of x, then the derivative of f with respect to x is another function that gives the rate of change of the original function, f of x. And I'll give you a couple of very simple examples of this. So let's stack a couple of sets of axes over here. On this top axis, I'm going to graph a function f of x versus the input variable x. And on the bottom set of axes, I'm going to graph the derivative df dx with respect to x. So let's say the first function is something simple looking like this thing here. So I'm trying to draw a horizontal line, a constant function. So whatever the input x is, the output is always some constant value. Well, that means the original function has no rate of change, or the rate of change is 0. So I would plot the derivative of that function on the axis below, and that would just go right along the horizontal over there. Okay, so again, this function has no rate of change. Its rate of change is 0, okay? And that means the rate of change of that function is 0, and I'm just plotting 0 along the axis below. Here's another example. I'll use orange. Okay, so let's say I have this function. Actually, orange is a terrible choice. It doesn't contrast with the red very well. How about purple? This purple function has a constant positive rate of change. You can see by now I'm referring to the slope graphically. So a constant positive slope, and that means its derivative has a constant positive numerical value. If I have a steeper, let's say something like this, it's a bigger slope, right? If I have a steeper linear function that I'm plotting, then its derivative will be a higher valued constant positive number. All right, so those are some, well, let me do one more for completion here. Let's say I'll use green. Let's say I have a function that has a constant negative slope, then its derivative will be a constant negative value like this. All right, so the slope of a function is the value of the function's derivative. Okay, so let's take a look at some numerical examples now. Let's say I have the following function. F of x equals, let's say 2x squared plus 6. All right, so the function is 2x squared plus 6. You should know what this looks like. It looks like a smiling parabola that intercepts the vertical axis at f of x equals 6, just like that. All right, now what does the derivative of this function look like? Well, the first thing to note is that the derivative of this function should have a value that matches the slope at every x value, every input value. So I'm going to plot df dx over here. Let me adjust the lights 1 moment. Lights in the classroom are on a motion sensor, so they go off. All right, so if I look at the original function here, 2x plus 6, the first thing to note is that the function is decreasing. It's got a negative slope for negative x values, and then it's increasing. It's got a positive slope for positive x values, and it's got a slope of 0 at x equals 0. So there's one numerical value I can plot right away if I'm trying to graph the derivative of f with respect to x. That is, at x equals 0, the slope of the original function there is 0, and so the derivative value is 0. And the slope to the right of x equals 0 gets bigger, steeper, bigger, steeper. So the rate at which f of x changes itself increases as x gets larger, because the slope of the original function, as I go this way, gets larger and larger. It turns out that the slope of a parabola linearly increases as you go from left to right. So at greater and greater x values, the output of this function is quadratically increasing, but the slope of the function is just linearly increasing. And as you might expect, as I go to the left, the slope is getting more negative, more negative, more negative. Moving to the left, the slope of the function above is getting more and more negative, and it's actually getting more and more negative also in this linear fashion. Now, what is this function that I've just plotted over here? Well, this is actually the function for x. It's just a line that goes to the origin with a slope of 4. How do I know that? Well, what's important is, how do I get that result, given I know what the original function is? I'm going to show you how to do that right now. Whenever the function that you're dealing with is a polynomial, such as 2x squared plus 6, there's a simple rule that you can apply, an algorithm you could apply to obtain the derivative function. Let me show you what that looks like. So the original function is f of x equals 2x squared plus 6. So what do I do with this thing? Well, I apply something called the power rule. I take the exponent of the variable x, I bring it down and I multiply, and I turn the exponent into an exponent that is 1 less. I demote the exponent, so to speak. So 2x squared, I'm going to bring the 2 down and multiply out front, and then demote x to x to the first. What about that constant term? Well, the number 6 can be thought of as 6 times x to the 0. X to the 0 is just 1, so 6 is the same as 6 times x to the 0. So I bring down the 0 and multiply, and well, I guess I could think about demoting this to -1, but the important thing here is that when I bring down the 0 to multiply, the whole thing gets wiped out. I'm multiplying by 0. So I end up with 2 times 2, which is 4, times x to the first, which is x, and this is what we call df dx, the derivative of the function f with respect to the variable. Okay, let's look at this with a slightly more intricate example. So I'm actually going to stack 3 separate axes here. Here's the first axis, 3 sets of axes. There's one. Here is another. Trying to draw this as cleanly as possible. And here is another. All right. Now, what function are we dealing with? I have to tell you. Let's look at the function f of x equals negative x cubed plus 2x squared plus 15x. Okay, what does this function look like? Well, it's a cubic function. It's not so easy to figure out exactly what it looks like, but you can use a graphing calculator or you can use Desmos. And if you do that, you will discover that the function looks something like this. Okay, that's what that function looks like. And now we're interested in figuring out what the derivative of this function looks like. Now, I could apply the algorithm that I just applied before, which is called the power rule, and bring down the exponents and multiply out front and demote the exponents of each term of that polynomial. But I just want to point out, first of all, that at this x coordinate and this x coordinate, the rate of change of the function, with respect to the variable x is 0, plotting df dx down here. So if I just come down with a line, I know at this x coordinate and at this x coordinate, the slope of the original graph is 0, so the derivative of the function has a value of 0. Derivative of f with respect to x has a value of 0. Okay, well, I know there are only 2 roots to the derivative. That's something to think about what that might look like, but let's apply the power rule now. All right, so the original function f of x. So I bring down the 3 and multiply out front. So that first term is going to have a negative 3, and then I demote x cubed to x squared. Then I bring down the 2 and multiply out front. 2 times 2 is 4, and when I demote x squared, I just get x. Then there's a hidden 1 over here. I bring down the 1, I multiply out front, and I just get 15, x to the 0. 15x to the 0 is just 15. So it looks like I have a parabola over here. Indeed, I do. I have a quadratic expression. Note, I started with a cubic, a third-order polynomial, and I end with a quadratic, a second-order polynomial. And what does that parabola look like? I'll show you what it looks like. It looks something like this. Try to draw this accurately. Sorry, that is totally inaccurately. I will draw it like this. Let me try that one more time. Okay, good. This is the derivative of f with respect to x that I've just drawn. Let me highlight a few things to convince you that this actually makes sense. Well, first off, to the left of this red line, so in this region, you should see that the original function has a negative slope everywhere there. And the value of that slope is given by the value of the derivative of f with respect to x. So the negative slope to the left of that first red line corresponds to the negative values of the derivative. Then in between these 2 red lines, I see the function has a positive slope, and the value of the derivative of the function with respect to x has positive values that match those slope values. And then to the right of the rightmost dashed line, I see the function has a negative slope everywhere, and the derivative has negative values everywhere. This is the most important thing to appreciate. It's the slope, the rate of change of f of x, that determines the numerical values that you're plotting when you plot the derivative of f with respect to x. Whoops. Okay, there's one more thing to appreciate here, which is this location is the location where you have the biggest positive slope on the original function. Focus in on that location right there. the slope of that function is the same as the slope of the tangent line to that function at that point. And there is no other point on this function that has a bigger positive slope other than the one I've identified. That means the derivative of this function should have its biggest positive value at that location. Indeed, that's the vertex of the parabola. The largest positive value of df dx is achieved at the same x coordinate as where the original function has its biggest positive slope value. Okay, so if somebody were to ask me, let's say, what is the slope, the rate of change of f of x at x equals 1. Let me get the lights again. If someone were to ask me, what's the slope of f of x, the originally plotted function on top of the screen, at x equals 1, what I would do is I would compute the derivative of f with respect to x, which is this parabola, and then I'd plug in x equals 1. The way I would symbolically write that is like this. df dx evaluated at x equals 1 is equal to -3 times 1 squared plus 4 times 1 plus 15. This is -3 plus 4 plus 15. This is equal to 16. So at x equals 1, the original function is increasing at a rate of 16 with whatever units apply, if any. All right, we can go one more step. We can plot the second derivative of f with respect to x. Notice how I'm writing that. I'm writing d squared f dx squared. For now, that's just notation. And you should remember what that notation looks like. The second derivative of the original function with respect to x is written as d squared f over dx squared. As you might expect, to compute the second derivative of the original function with respect to x, we can just find the first derivative, or just the ordinary derivative of the derivative of the original function. So df dx is something we already computed. It's -3x squared plus 4x plus 15. If I want to find the second derivative of f with respect to x, I apply the power rule to this function. Why don't you pause the video and take a moment to do that? Okay, if you were able to accomplish this, congratulations. Or if you're just here for the show, the 2 gets brought down, so you get -6. X squared is demoted to x to the first. There's a hidden 1 here, which gets brought down. 1 times 4 is 4, demoted to x to the 0, which is just 1. And the 15 gets wiped out because it's like 15x to the 0, and you're bringing down the 0 out front. So this is a linear function. This function here is a linear function with a vertical intercept of 4, and it looks something like this. -6x plus 4 just looks like that. I think it'll be easier to appreciate the relationship between a function and its derivative by looking at these two functions. The bottom function is the derivative of the middle function on the page, but the top function between those two at the bottom of the page. So let's see. It looks like I have a slope of 0 here, so the derivative isn't changing. And that means the derivative of the derivative has a value of 0. Furthermore, the slope is positive here, so the values of that function's derivative are positive here. And the slope values are becoming increasingly negative as I move to the right, so the values of the derivative are becoming increasingly negative. So these functions might represent a whole bunch of things. For example, it might be the case that this top function is position, and this next function is velocity, and this next function is acceleration, because that is the relationship between position, velocity, and acceleration. Although, if this were the case, I would have to be plotting these variables versus time. The derivative of position with respect to time is velocity. The derivative of velocity with respect to time is acceleration. If you're not convinced of this, let's see how this statement is consistent with our kinematics equations. So last year, you learned that these are the constant acceleration kinematics equations. We only need the first two over here. So these are what we called kinematics equations 1 and kinematics equation 2 last year. Well, the x component of the velocity is just the derivative of position with respect to time. It's the slope of the position versus time graph. It's the rate at which the position changes with respect to time, usually in meters per second. So let's see how this works. We have x initial. There is no time variable there. It's really like t to the 0, right? So when I bring down the 0, that first term gets wiped. This is like t to the first. So when I bring down the 1 and multiply out front, I just get v initial sub x. T to the first becomes t to the 0. So that becomes a v initial sub x times 1. Plus, when I bring down the 2 and multiply out front, I get 2 times a half is 1 times a sub x. And t squared gets demoted to t. Well, look at that. I took the derivative of the position function with respect to time by applying the power rule, and I obtain the velocity function, which is consistent with kinematics equation number 2. It works. I want to make one comment now about notation. So for the first derivative, the notation actually has some deeper mathematical meaning. If I have a function f of x, then we say the derivative of that function with respect to x is a new function, df dx. Let me take a moment to talk to you about the significance of that df dx. All right, so if this is f of x and this is x, and suppose my function looks like this, and let's say I want to find the derivative at this point. Well, one thing I could do is I could select two other points that are to the left and to the right of that point there and connect them with a line. And I have a little triangle here, and this triangle has a height delta f. That's the change in the output value between those 2 points, and it's got a base delta x, which is the change in the input value between these 2 red points. Now, the slope of the hypotenuse of this little triangle is not quite the same as the slope of the function at that location. If I were to slide this point and this point closer and closer, though, to the point of interest, then the slope of the hypotenuse of this red triangle would better and better mimic the actual slope of the tangent line, the slope of the function itself at this critical location. So I could say that df dx is the limit as delta x approaches 0 of delta f over delta x. This is how you calculate slopes between 2 points in general. You find the change in y, or the change in f in this case, and you divide by the change in x. What we're doing is we're shrinking this delta x interval down until the 2 points collapse into the single point of interest. And so we should interpret df and dx as infinitesimal changes in f and x. Delta f is like a macroscopic jump or change in the function f. Delta x is a macroscopic jump in the input value x. And if I shrink those intervals down, I get the ratio that I call df dx. Now, an infinitesimal quantity is not equal to 0, but it's well, this is not mathematically rigorous, what I'm about to say, but it's as close to 0 as it can be without being 0. So df dx, the little change in f over the little change in x, it's really like shrinking the numerator and the denominator down to 0 and seeing what the ratio is, the ratio being the slope of the function at this point. Sometimes people look at this and they say, wait, if dx is like really, really tiny, it's like delta x, but shrunk down to 0, like isn't dividing by 0 a problem? Sometimes dividing by 0 is a problem, but sometimes is not. For instance, if I take the limit as t approaches 0 of the expression 4t divided by t, then as t approaches 0, the denominator is going to 0. It's shooting down to 0, but so is the numerator. The important thing is as the variable t shrinks down to 0, the ratio of 4t to t is just the number 4. The t kind of cancels out. So you can divide by a quantity that is approaching 0, so long as the numerator is also approaching 0 and end up with just a finite number, like the number 4. And that's what's going on in this example. One moment, the lights went out again. All right, so at the beginning of the course, we will be making use of derivatives. We will be applying the power rule in order to calculate the derivatives of polynomial functions. And we'll be obviously dealing with functions other than polynomial functions in the course. But I think this is the bare minimum that you need to appreciate in order to not get tripped up with derivatives in the beginning of the course. I hope this video is helpful to you, and I'm still working out what this summer packet work is going to look like. I may give you some practice problems, and if I do, that'll be posted on Google Classroom along with this recording. Have a good one.